Hi everyone, welcome to lecture 39. I know it says on the notes lecture 38, but it's actually lecture 39. We're going to be talking about the Brayton power cycle today. So in the previous couple of lectures, we've talked about the Rankine cycle improvements. Then we talked about air standard analysis, Otto cycle, diesel cycle, and a dual cycle. Now we're getting into the Brayton power cycle. We'll have this lecture and the next one talking about the Brayton power cycle, and then the very last lecture will be a review, and then we're at the end of the semester. So you're very close to wrapping up the course. Today we'll be talking about this Brayton cycle. So the application is really gas turbine engines like what you see on the screen here. The top picture is of a cutaway gas turbine engine, and then the bottom picture is just a schematic, kind of a cartoon of the same device. So what happens in this kind of a gas turbine engine is you have air coming in from the left side, moving toward the right. For a jet engine application, there would be a diffuser here actually at the inlet right before the compressor. The purpose of the diffuser is to slow the flow down and also increase the pressure a little bit. The reason you want to slow the flow down is when the air comes in here, maybe at high velocity, and then as the blades are turning, it's even a higher relative velocity. So what ends up happening is you could reach supersonic speeds relative to the blades. And when you reach supersonic speeds, so that means speeds faster than the speed of sound, what happens is you can get shock waves that form, and those shock waves can cause mechanical stresses on the compressor blades, and that's undesirable. So the diffuser helps to slow the flow down and also gives you a little bit of increased pressure. And of course, the compressor, the whole function of it is to increase the pressure, so we get a little extra higher starting pressure when we diffuse the flow. So the flow comes in, it goes through these compressor blades. So there are actually several stages of compressor blades. You can see them here. You can see them in both the cartoon and in the actual picture. The pressure rise across each set of compressor blades, each stage is about 1.25, just as a general rule of thumb. So there's just a 25% increase in the pressure across each stage, and then you have multiple stages so that the total pressure rise can be much higher, somewhere maybe on the order of a factor of 5 up to a factor of 20, depending on how many compressor stages you have. The purpose of the compressor, of course, is to increase the energy in the fluid, which is in this case air. So you increase the pressure and you increase the temperature as it goes through the compressor stages. And actually what's not shown here is in between each compressor blade is actually what are called stator vanes or stator rows. So it's a little hard for me to draw on this, but there'd be some blades in between. Actually, it's probably easier down here. So there'd be some what are called stator vanes that are connected to the housing. And the purpose of those, and those would be all the way around, just kind of like the compressor blades themselves. So they would be in between each set of blades for the compressor. And so the compressor blades are rotating, obviously, because of the rotating shaft. They're airfoil shaped, and the purpose of each compressor blade is to increase the pressure in the air as they go past here. The stator vanes, which are the fixed vanes here, they don't rotate. The purpose of those is to redirect the flow. So once the air goes through these spinning compressor blades, it's changed direction, and the stator vanes try to redirect the flow so that the flow velocity is in the optimal angle when it comes into the next section of compressor blades. So it helps redirect the flow to make the flow ideal for the next set of blades. In addition, those stator vanes, they're shaped such that they diffuse the flow a little bit. They take a little bit of the kinetic energy and put it back into pressure, just like a diffuser. And so you get a little bit of pressure rise across the stator vanes as well. So the combination of rotating compressor blades and stationary stator vanes helps increase the pressure as you go through that whole compressor stage. Once you're through the compressor stage, you move into the combustion chamber here. And here's where the fuel, the jet fuel, is mixed in with the air, so something like kerosene. You can see the corresponding picture up in here. And then it's ignited, so you can see a little spark ignition here that would ignite the fuel. That's where you add in a lot of energy, right? So you're combusting some fuel. It's like a heat addition process. The pressure through here is modeled as being a constant pressure, but the temperature goes up quite a bit because we're adding a lot of energy through the combustion process. Once you come out of the combustion chamber, you go through a series of turbine blades. Again, these are rotating around, and in between these you would have some stator vanes as well to help redirect the flow into a more ideal direction coming into the next stage of turbine blades. The purpose of the turbine is to provide enough power to drive the compressor. You can see that the turbine is connected to the compressor via a shaft here. You can see it there, and you can see it here as well. And the idea is you want to extract some energy from the high temperature, high energy combusted products that come out of the combustor, extract some of that energy from the turbine to drive your compressor stage. And then you might have a little bit of energy left over to power electronics, avionics, things like that in your aircraft. You don't want to pull all the energy out because you still want to have some energy in the flow that you can then turn into kinetic energy via a nozzle at the exit. So right at the exit, there's typically a nozzle so that you get a high velocity. You want the velocity coming out of the back end of this thing to be as high as possible for a jet engine so you get a lot of thrust. That's the whole point of a jet engine, is you want to take that energy that you've added into the flow through the combustion process here and turn it into kinetic energy out of the back end so you get a lot of thrust. The idea behind thrust and how you analyze that is discussed in ME 309, the fluid mechanics course, so we won't discuss it here. But usually there's a nozzle here that accelerates the flow and turns some of that thermal energy into kinetic energy. Sometimes there are other components that are included in a jet engine design, so you might have an afterburner here. That's where you add in a little more fuel and ignite it and get even more energy into the flow and turn that into a velocity. You might have some fan blades upstream here that are like compressor blades, but they don't have quite as much pressure rise across them. So there are variations on these designs. If you want to know more about how jet engines work, there's some videos here. The first video is just a basic overview, kind of like what I've discussed here. The second one is more of a hands-on, where a person walks along a jet engine and kind of points to some various parts on the jet engine. And of course, there are many other YouTube videos that are available online, so I encourage you to take a look at those. So the way we analyze the Brayton cycle, we will follow the same approach we've taken in other cycle analyses. We use a first law analysis and calculate efficiencies and things like that. So the schematic for the Brayton cycle looks like what we have here. On the left-hand side, we have an open gas turbine cycle. It's a Brayton cycle. And then on the right-hand side, we have a closed one. Let me start with the closed one first. So we have a compressor that compresses our working fluid. That goes into a heat exchanger. This is really our combustor, where we're adding heat coming into it. It's a constant pressure process from 2 to 3. Then we go through the turbine, where we extract some energy, and the pressure decreases. We explicitly show the connection between the compressor and turbine in this picture because that's how it's designed in like a jet aircraft engine, that they're on the same shaft. So we really want to emphasize the idea that the turbine is driving the compressor in the cycle, and then you can get some extra power out of it here. And then in the closed gas turbine cycle, we come out of the turbine, we go through a heat exchanger to get rid of the heat. Remember, we need to do that from the second law. So this would just be cooling the working fluid down to get it back to state 1, and then we repeat the cycle. So this is a true cycle because we keep going around in circles here. The open gas turbine cycle is shown on the left-hand side. It looks pretty much the same, but what I've done is just grayed out the heat exchanger part. In an open gas turbine cycle, this really reflects what's happening in a jet engine. In a jet engine, the working fluid, which is the air, doesn't go around in a cycle, right? It comes in from the atmosphere here, and then when it comes out of the back end of the engine, it goes back out into the atmosphere. So it's not technically truly a cycle because you have new air coming in and then old air going out. It's not being recirculated. But you can imagine that it's being recirculated. You know, the atmospheric air eventually goes back to being whatever the temperature is at the inlet. The atmosphere is a huge reservoir, so we're always bringing in air at the same conditions. It's almost as if we come out of the back end of the engine, go through the heat exchanger, and then come back in so that we get back to the atmospheric conditions. So it's not a true cycle, but we treat it like a cycle, and that's why I've grayed out the heat exchanger, because it's kind of like we're going through that process, but in reality we're not. We're just pulling in new air from the atmosphere and continuing through. One thing I'll mention at this point is one of the design specifications typically for the gas turbine cycle is the pressure rise across the compressor. So we're often designed for a particular pressure increase. P2 is greater than P1. And since we're pulling air from the atmosphere here, and then we're discharging air back into the atmosphere, the P1 and the P4 are treated as being the same. And then also, since the combustion chamber is a constant pressure process, we also know that P3 is equal to P2. So the pressure P3 over P4, you can quickly see, is equal to P2 over P1. Okay, so we're going to make use of that information a bit later in the lecture. The other thing is that the highest temperature in this whole cycle is at state 3. So T3 is the maximum temperature in that whole cycle. It's the temperature when we come out of that combustion chamber. So it's the highest temperature. That maximum temperature is an important quantity. It's related to the thermal efficiency of the cycle, And also it impacts how the turbine is designed. You can imagine if you have your composite or metal blades in the turbine, you don't want to melt those. If T3 is too large, then you could weaken those turbine blades, and you don't want to have turbine blades that are very weak and could fail. So T3 is an important quantity just from an engineering perspective so that you can design equipment to withstand those high temperatures. Okay, so the way that we analyze this Brayton cycle is we'll use an air standard analysis. You're familiar with this already. Working fluid is air. We treat it as an ideal gas. We allow the specific heats to vary. Let me make a note of that. Specific heats can vary with temperature. The combustion process up here in the combustion chamber is modeled as a heat addition to the working fluid, a constant pressure heat addition. We won't model the chemistry involved in that combustion process. We won't worry about the fact that the air-fuel mixture has a different set of properties than the air coming in. This is a simplified analysis. And then in some cases, we do a cold air standard analysis. In that particular type of analysis, the specific heats are constant. Okay, so the working fluid is treated as a perfect gas in that case. The cold air standard analysis is really only useful for looking at trends and qualitative behavior. Especially in a Brayton cycle, the temperature difference between the inlet at state 1 and T3 is pretty large. Hundreds, if not 1,000 Kelvin difference. So assuming constant specific heats is not a very good assumption. Nevertheless, we do sometimes make this cold air standard analysis just so we can gain some understanding of what parameters might be important, what kind of trends we're going to have, that sort of thing. But numerically, you're better off just using an air standard analysis where the specific heats can vary. To analyze the performance of this Brayton cycle, we'll use our usual approach. We can draw control volumes around the turbine and the compressor and apply the first law. Some of the things that we assume here is steady state, steady flow, adiabatic conditions, and negligible changes in kinetic energy and potential energy, right? And then if you do all those things, one inlet, one outlet, you get these expressions for the power coming out of the turbine and the power going into the compressor, and they're functions of these specific enthalpies. You can do the same sort of first law analysis on the heat exchangers. This is the combustor here, where the heat's added. This is the heat exchanger right there, if you're interested in that part. You can find the thermal efficiency of the power cycle just using our normal definition, where it's the net power out, which is the power generated by the turbine minus the power going into the compressor, divided by the heat added in the combustor. And you could express that in terms of your specific enthalpies if you'd like, so kind of show the algebra involved here. Or another way to do it is you can just use the first law and do it in terms of the heat transfers. So all of this is stuff that you've already seen before. There's nothing new here. We do have one new definition here, and this is a thing called the back work ratio. So BWR, the back work ratio is defined as the power that goes into the compressor divided by the power that comes out of the turbine. Or if you make use of our first law expressions up here, you can put it in terms of specific enthalpies. Now the back work ratio just tells us how much of our power that we're generating is going into the compressor. For a gas turbine engine, it's actually a pretty large number. I say here 40 to 80%. Especially when you think about it for an aircraft. You only want to generate enough power out of your turbine to drive your compressor, and then maybe a little extra for avionics, etc., things like that, right? There's no point in oversizing your turbine to generate a whole lot of extra power that you're not going to use. In fact, on a jet engine, you don't want to pull all of your flow energy out through the turbine because you want to have a lot of energy left over to turn into kinetic energy out of the back end, right? So you don't really want to oversize your turbine. However, in a power plant operation like a Rankine cycle, a vapor power plant for generating household electricity and such, there you do want your power coming out of the turbine to be a lot more than the power going into your pump. So remember that in a power plant, your compressor, your pump. It's when you're dealing with a liquid, we call it a pump. There, the back work ratio is much smaller, 1 to 2%. You want a large amount of power coming out of your turbine so that you can use it to power your households and things like that. you don't want to have to put a bunch of that power back into your pump. So that back work ratio is much smaller. So I mean, that's a desirable trait of a vapor power plant as opposed to a gas turbine. Now the reason that they're so different has to do with the fact that the working fluid in the gas turbine engine is a gas, and the working fluid for the Rankine cycle in the vapor power plant is a liquid. Now why does that make a difference? Well, if you go back to your notes, I think it's lecture 32. I'll put a question mark. I'm not quite sure which lecture it is, but the lecture where we derived Bernoulli's equation. You recall that when we started with the first law, combined it with the expression for heat transfer for a reversible process, if we were dealing with a steady flow that's internally reversible, one inlet, one outlet, and negligible changes in kinetic potential energies, then the power generated in that flow was related to the specific volume times the change in pressure. Actually, I'm going to rewrite that to put it in terms of the compressor. So rather than being by the CV, I'm going to write it as W dot in to the CV. So when I change it from by to in, I'll get rid of the minus sign. And instead of writing it in terms of power here, I'm just going to put it in terms of specific work. Specific work is just that power divided by mass flow rate. So the specific work that we have to put into our compressor or our pump is going to be related to VdP. Now normally, as I mentioned at the beginning of the lecture, the pressure rise across your pump or across your compressor is specified. So we know how much pressure rise we typically would need to have, but we need to multiply that by our specific volume of our working fluid, right? So as our specific volume increases, then our specific work increases, right? For given pressure rise. Now the specific volume for air is actually quite a bit larger than the specific volume for water. Remember that in the vapor power plant, when we go through the pump, it's water, it's liquid water, right? So the specific volume for air is much larger than the specific volume for water. Another way to think about it is in terms of densities. The density of air is about 1,000 times less than the density of liquid water. And remember that specific volume is just 1 over the density. With that in mind, you can see that the specific work for the Brayton cycle, which uses air, is going to be a lot larger than the specific work for the Rankine cycle, which uses liquid water. And that gives rise to our differences in the back work ratio, because for the vapor power plant, our work that goes into the compressor, or our specific work going into the compressor, is really small compared to what it would be for the Brayton cycle because of this effect. So it really comes down to the differences in the specific volume of the working fluids, and that gives rise to these big differences. Okay, that's an important concept. Make sure you understand that. All right, so let's go through the different processes in the ideal air standard Brayton cycle. So ideal meaning that our isentropic efficiencies for the compressor and the turbine are 100%. So from 1 to 2, that's going through the compressor. That's an isentropic compression. It's probably easiest to see over here on the TS diagram. So from 1 to 2, this one is through the compressor. So we're going to compress our working fluid. The actual process, there's going to be some increase in entropy, so that's why state 2 is a little bit off to the right where the entropy increases a bit. You can see that we go from a low pressure to a high pressure. You can see our different isobars. If you do this on a PV diagram, you can see state 1 here. Then we go along a constant entropy line to state 2, where the pressure is higher. You can see that we're moving right to left on this, right to left, because we're compressing the gas. And then from 2 to 3, that is the constant pressure heat addition process. This is, it says through the heat exchanger, but really it's the combustor. That means that we're going along our isobar from 2 to 3. That's where the pressure is constant. So this is our combustor. This is where we're adding in energy via heat transfer. You can see this over on the PV diagram, 2 to 3 constant pressure process. Then from 3 to 4, we have isentropic expansion of the working fluid through the turbine. So we're moving through the turbine here, so that's this part. And again, if it's an ideal turbine, 100% isentropic efficiency, we go vertically straight downward. You can see, S3 equals S4S. Same sort of thing over here. In the real case, we would be moving off to a little bit higher entropy if we had a less than 100% isentropic efficiency. So when we go from 2 to 3, that's along the same isobar. When you go through the turbine, the pressure decreases. So we're now back on this isobar, so the pressure is less. And you can see that over on the PV diagram. We go from a high pressure back to a low pressure along a constant entropy line. And it's an expansion. We're moving from left to right with specific volume. It's expanding as you go through the turbine. And then from 4 to 1, that's going through that heat exchanger, or if we're dealing with a jet engine, it's kind of an imaginary heat exchanger, so we could do it as a dotted line. And that's a constant pressure process to start the cycle over again. All right, that's what it looks like on a TS and PV diagram for the Brayton cycle. As far as the actual analysis, so if we do the air standard analysis, we're assuming the air is an ideal gas. And from process 1 to 2, that's a constant entropy process. You can see that that's vertical. Same with 3 to 4, constant entropy. So if you're dealing with an ideal gas in an isentropic process, we can use these relative pressures to find how the temperature changes. So P2 over P1, that's usually a design parameter. That's a given. To find the relative pressure at 1, you can use the ideal gas table for air to look up that value. If you know T1, typically you know that. That's a boundary condition. You typically know that. So you know the incoming temperature. You find the relative pressure at that temperature from the ideal gas table. P2 over P1 is typically a design parameter that's given to you. You're designing your compressor to give you that much pressure rise. Then you can solve for the relative pressure at T2S, and then you can use the ideal gas table to find the temperature at state 2S. You can do a similar sort of thing from 3 to 4, like going through the turbine. Remember that the pressure ratio from 3 to 4 is the same as pressure ratio from 2 to 1, right? Because you're going from atmospheric conditions to the combustor pressure. Pressure across the combustor remains the same. Right? We're going from atmosphere to 2. Pressure across the combustor remains the same, and then at 3 to 4, you're going back to atmospheric. So this is how we had the pressure ratios are the same. So we can make use of that information to find, P4 over P3, and then we can do the same idea dealing with an ideal gas undergoing an isentropic process. We can use the relative pressures to find ultimately T4S. Temperature 3 here, T3, is typically a known quantity. Again, it's kind of a design quantity. What is the temperature you get out of your combustion process? That's typically a given quantity or something you find from some other analysis. If we were doing a cold air standard analysis, then what we could do is assume that the specific heats are constant, and so that means that we're dealing with a perfect gas. If it's undergoing an isentropic process, then we can use these isentropic relations for a perfect gas, so getting the temperature ratio in terms of the pressure ratio. Again, this is not the most accurate way to do things because we have large temperature differences, but it's convenient for just qualitative understanding. So that's how you would analyze what's happening across the compressor, across the turbine, and of course through the combustor, we can always apply the first law through the combustor to see what the heat addition is and how that's related to T2 and T3. If we want to find the efficiency for the cycle, of course, if it's an ideal, it's kind of an air standard analysis, just an ideal gas, the efficiency will be the net power out. So that's the power coming out of the turbine minus the power going into the compressor divided by the heat coming in through the combustor. So we can use our standard analysis for that. So that part of the process, if you go back here and look, you can see we've already done that derivation here, and it's in terms of H4 minus H1 and H3 minus H2. So that's just been repeated right here. If you're doing a cold air standard analysis where the specific heat is a constant, we could write delta H in terms of Cp delta T, and then do a little algebra on this, and then ultimately what you see is the efficiency for the cold air standard analysis is related ultimately to the pressure ratio across the turbine, as well as the specific heat ratio. K is your specific heat ratio of your working fluid, your air, for example. So the higher the pressure ratio, the more your thermal efficiency, the higher your thermal efficiency. Another way to look at it is the higher the value for T3. Remember, T3 is your maximum temperature. It's the temperature out of the combustor. So as T3 increases, you can see that the efficiency will also increase, right? If the denominator here gets bigger, then this whole quantity gets smaller, and then you approach 1. So a couple of different ways you can think about the efficiency. Larger compressor ratios give you higher efficiency, or a larger temperature out of the combustor gives you a higher efficiency. So typical pressure ratios, I've mentioned this at the beginning, across the compressor are between 5 and 20. So you get typical efficiencies on the order of 35 to 60%, pretty high. A larger pressure ratio, we just said, gives a larger efficiency. Another way to think about it is increasing the temperature leading into the turbine or out of the combustor also leads to a large efficiency. However, the temperature at the turbine inlet's typically limited by metallurgical considerations. So this goes back to something I said at the beginning. If you have a really high temperature leading into the turbine, one of the things you have to worry about is softening of the turbine blades. As you get to higher and higher temperatures, you're starting to approach the melting point of the materials, and you certainly don't want that. So there's a limit to how high the temperature can be. So there's a limit to your efficiency, just due purely to metallurgical considerations. So there's been a lot of research that's gone into the material science of turbine blades. They have stiff turbine blades at very high temperatures. There's some other kind of neat engineering things that people have done with turbine blades. So for example, I'll sketch here a turbine blade. It's a very rough sketch. The turbine blades look kind of like airfoil shapes. And you've got your hot air coming in, at temperature T3. It's very hot. So one of the design features that they actually implement in most turbine blades is they'll have these little injection ports on the blade at strategic locations. And these are connected to some of the incoming air coming into the engine. So they bleed off some of that air coming into the compressor, and it's at a relatively cold temperature. Then they feed it into the turbine blades through the base of the turbine blade, and it comes out of the blade. And what it does is it creates this kind of cold boundary layer of air along the surface of the turbine blade, so that you can still have a high T3. You have this hot air kind of flowing around your turbine blade, but very close to the blade itself, it's relatively cool because you have this kind of insulating cold layer of air next to the surface because you've injected it in. And that way you can get to even higher temperatures than you might be able to otherwise because you have that cool thermal boundary layer. So kind of a neat engineering design to help improve efficiencies. Okay, so now let's consider the case where the T3 temperature is fixed. We just talked about that. You can only go so high. So what we're going to do is have this fixed upper bound for T3. What we're doing is we're looking at a Brayton cycle on a TS diagram. And then what we're going to do is we're going to look at two different Brayton cycles with different pressure ratios. Okay, so the first one we'll call cycle A goes from state 1, state 2 prime, state 3 prime, which is our limit, down, and then repeat the cycle. So this is our cycle A. And notice that when we go from 2 prime to 3 prime, that's a particular isobar, right? That's our P 2 prime 3 prime. It's a particular isobar. And then the second cycle that we'll consider is going from 1 to 2, not to 2 prime, but just to 2. Then we go along this isobar, then down and repeat the cycle. So this is cycle B. Now P23, that pressure is going to be less than P2 prime 3 prime because just our isobar is lower, right? So we have different pressure ratios. That just means that P23 over P14 is less than P2 prime 3 prime over P14. So you would expect then that the efficiency for cycle A will be larger than the efficiency for cycle B because of the pressure ratio being larger. We've talked about the pressure ratio being a factor right up in here, right? The larger the pressure ratio, the higher the efficiency. the efficiency for cycle A, let me keep the colors consistent. Efficiency for cycle A will be greater than the thermal efficiency for cycle B. That's one way to think about what's happening here, is you can concern yourself with thermal efficiency, and of course cycle A is better than cycle B for that case. Now another way you can look at these cycles is how much specific power you generate in the cycle. Remember that for an ideal cycle, the heat added, the specific heat added, since it's ideal, it's reversible, will be the integral of TdS. It's the area underneath the curves in our plot. So like, just remember, I'll draw it over here. So Ts, you have some curve here. This area underneath, that's our integral of TdS, which go from 1 to 2. And that'll be the specific heat in. It's only true for a reversible process. But since we're dealing with an ideal Brayton cycle here, it's all reversible, so it's fine. The area under these curves is related to the amount of heat added, right? So from 2 to 3, we're putting in heat because we're going from left to right. From 4' to 1, we're removing heat. So the area inside here is related to the net heat addition that you've put in. So let me kind of highlight that. So that's the net heat addition for cycle A, and then the net heat addition for cycle B will be this one. Okay, so that net heat addition is also related to the net work, right? From the first law for a cycle, remember we're doing this over a cycle, change in the internal energy is 0. Here we have our the net heat coming in, and this will be related to the net work coming out. I'm doing these all in terms of specific quantities. So the net specific work out will be just related to the net heat that we put in here. So the orange kind of highlighted region and the blue highlighted regions will be related to the net specific work coming out of the cycle. So you can see then in this picture, the area, apologize for that noise, the area B is bigger than the area for A, and so the specific work for B is going to be bigger than the specific work for A. So the thermal efficiency for cycle A is higher, but the specific work for cycle B is larger. Now, in an aircraft engine application, generally what you want to do is you want to keep all of your mechanical components as small as possible, because the smaller they are, the less weight you have, and you want your aircraft to be as light as possible so you don't have to go through as much fuel. So generally you would be better off designing for improved specific work so you can keep everything smaller to get the same power out of your cycle than if it was bigger like this, right? So you want to keep everything as small as possible, so you want your specific work to be as much as you can get out of your components. The thermal efficiency is secondary. It'd be nice to have higher thermal efficiency, but for an aircraft application, weight will be a very important thing to consider, another engineering consideration. So what typically dominates is having a larger specific work as opposed to a higher thermal efficiency. Well, anyway, that's just another engineering related matter. The very last thing I have here is the influence of the specific heat ratio on the efficiency. This goes back to this relationship here. You can see the specific heat ratios up here. If K is larger, you tend to have larger thermal efficiencies. The way you get larger K is you change the kind of fuel that you would put into your Brayton cycle. It has some effect. It's not one of the knobs people typically turn. It's what people typically modify is the pressure ratio. Changing the specific heat is not as much of a factor. But it does make a difference, so I thought I would mention it here. All right, so that does it for lecture 39 on Introduction to Brayton Cycle. The next lecture, we'll talk about Brayton cycle improvements, so some things we can do to get a little bit of extra thermal efficiency out of the whole cycle.